Now that we've spent some time thinking through whether a correlation, so a pattern between two variables, which is correlation, may or may not be causation, I thought I'd take some time to list off some possible reasons that you might see a correlation between two things, call them A and B, that might not be causal. So it might not be that A is causing B. Some possible reasons could include that it's actually the opposite being true. It might be that B is actually causing A, but you've just made the wrong assumption. It could be that A and B are correlated, but there's a little extra wrinkle that both of these things are being caused by something else. Call it C. So A and B are correlated because both of them are being driven around by something else. It could be because there's another variable involved in the process, maybe you haven't seen or thought about. So it could be that A does cause B, but only when some other event, call it D, has happened. Again, that'll give you a correlation between A and B, but that will suggest that it's not that A causes B, it's really that D is having some effect here that we need to understand. It could be that there's what I'm going to call a chain reaction. So that A causes something else, E, and then E is moving around, which is then causing B. But if you didn't know, and you only saw that A and B are moving around, and you didn't think about B because you didn't see it, for example, you didn't think about it, again, you make the wrong conclusion that maybe you'd think that it's A causing B, when it's not. All going through E. Finally, it could just be due to chance. You've just kind of lucked out in a bad way, and you found this pattern, but it's really just not there. You just somehow found something in some kind of process with two variables related, and they really shouldn't be in a causal way, but you haven't really got a concrete, it's like just statistical chance that you found that correlation. So the difficulty of causal inference and the difficulty of life as a marketing analyst who wants to make causal claims is thinking about, when can I make causal claims? When do I feel comfortable with the idea that the correlation that I may see in data is suggestive of a causal relationship? The first answer to potentially throw is, it's just hard, right? It's never going to be, or very rarely going to be, crystal clear and definitive, like beyond all kinds of reasonable doubt. You can get very close, but it's going to be hard, and there's going to be a lot of thinking involved. And that thinking is going to mean that it's going to be possible to get causation from looking at correlation in data, but you're going to need to be comfortable with some additional assumptions kind of added on top to be able to make this leap. What kind of assumptions do we need to make? There's two kinds of assumptions, what I've decided to be two kinds of assumptions. What I'm going to call the what would have beens kind of assumption, and what I'm going to call there must be some kind of as good as random assumption. So what do those two things mean? What could have beens mean to make causal claims from correlation, we need to be comfortable thinking that there's something in the data that we can think of as a counterfactual. If we didn't change X, then this would have been what we would have seen. And we have to be able to see it or approximately see it by making some assumptions on what that looks like. Second, this as good as random idea has a bunch of different names. Some people like to call it no selection on unobservables. Some others, more in the econ sphere of things, want to call it conditional independence. Essentially the same term. What's the idea of this as good as random effect? Or as good as random assumption, sorry. Well, what we need is that whatever's moving around the variable we care about, let's call it X for now, that variation in X that we're using to think about its correlation with Y, whatever's causing that X movement can't be due to some other factor, right? There cannot be something else in the background that we either observe or don't observe pushing around our X variable. That difference in the wiggling of X, the change in the variable that we're interested in quantifying, has to be essentially as good as random. So the variation is approximately random, not driven by something else. If we're willing to make that assumption, whatever is wiggling around X is randomness and not some unobserved factor, then we might be comfortable. We probably will be comfortable once we've really thought hard about that assumption. And there's a lot of thinking that we need to do a lot of the time, especially if we don't have experimental data. We're going to be able to say something about causal effect. And what we're going to be able to say is that we have what's known as an average causal effect. And what I mean by average is it's going to be the effect of X on Y, not for some specific individual in our sample, but averaged across individuals in our samples. It's not going to be an individual effect. It's going to be some kind of average of anything in our sample. So we're going to identify, at best, average causal effects. A bit of a misunderstanding that I think is common early on is you require some kind of statistical background, is that the regression assumptions that we saw last week on their own imply that the regression coefficients beta can have causal interpretations. That's not entirely the way I see it, and the way that most people see it. So the regression assumptions that we wrote down, or we read about last week, are going to tell us things about the unbiasedness of your coefficient, which is going to say that whatever partial correlation you may have found, the estimate of that is unbiased. And are also going to give you assumptions that let you say something about the variance of your estimate of beta. So how in repeated samples, your estimate of beta may move around. If you now want to say that unbiased estimate of beta, it's causal, have to be comfortable, you've got to be upfront and say it, that there's valid counterfactual outcomes in the data. So if X hadn't moved around by that, then Y might have been something else instead. And that there's conditional independence. So what's moving around the X that you care about, again, is random, not some unobserved factor that we haven't managed to model. Those two assumptions, valid counterfactual outcomes and conditional independence, are not something that you're going to be able to test, right? You're not going to be able to come up with a statistical method to test whether there's valid counterfactual outcomes in your data or whether conditional independence is satisfied. There are going to be assumptions that you have to think long and hard about, be comfortable making, and be prepared to defend, because if you're going to make a causal claim, most likely someone else is going to want you to be able to really defend that what you've done reveals a true causal effect. So you're going to have to be able to defend most probably conditional independence as the main problem quite rigorously. So you really got to be able to defend the idea, defend the notion, the variation in the X that you care about, that you're using to identify the change in Y, is as good as random. And there's nothing unobserved driving that movement in X. That's tough. And again, if you can think through this and when you can be comfortable making those claims, then you're going to have a lot of power in terms of the strength of things you're going to be able to say, but take some nuance in thinking about the story. Because that nuance is difficult in purely observable data, so when you're just like collecting data and looking at it. The recent trend in the applied marketing literature, so quantitative marketing or marketing analytics, has been to use experiments to estimate causal effects. Now, when I talk about experiments, I'm not thinking about experiments in a lab with students or running them online on a platform like mTurk, which might be what other people in the department think of as experiments, and when they toss around the terminology experiment, might be thinking about. What I'm thinking about an experiment is some kind of intervention in observational data that's random, or as good, or that where I put that intervention onto people or firms or whatever I'm trying to observe is as good as random. So these kind of experiments where I undertake some intervention in the real world, either by actually doing it or by finding some weird examples where nature seems to have given me some kind of intervention, are increasingly popular in marketing and in marketing analytics. So as I kind of hinted, there's two kinds of these experiments. First, we're going to call randomized control trials. It's also called A/B tests in tech companies. So what you're going to do as a researcher or as a marketing analyst, you're going to take your population, whether you're observing data from, and you're going to randomly assign some of those people, firms, states, provinces, something, to a treatment group where you're going to do some kind of intervention. For example, you might turn off advertising, or you might give certain people a discount in price randomly. And then there's going to be another group of people that you didn't give that intervention to. And you're going to use this idea of a treatment group where you gave them this shock, this intervention, and the control group, which didn't have this shock or this intervention. And you're going to use how the outcome variable evolves before and after that intervention in the treatment group versus the control group to compute some kind of causal effect. If you can't go into the world yourself and create these kind of interventions and shake things around, you could instead try and look for examples where nature or what we see in the world has divided the population somehow into a treatment and a control group where some people have had some intervention imposed on them and some people haven't. And the allocation of people into that treatment or intervention and those people not, it's not random, but it's as good as random, right? It's approximately random the way people were allocated to those events. Both of these approaches, you're going to compare changes in treatment and control groups over time to compute the causal effect of an intervention on an outcome variable of interest. How that happens, or how we do that, sorry, is what we're going to cover next.